Good morning to one and all. What I am discussing in pharmacokinetics. So, you read various definitions. Then the relationship between the plasmid drug concentration versus time. This is the very most important curve in your syllabus. Okay, then the third one is order of reactions. So in the previous classes I discussed you about this definition, plasmid drug concentration versus time profile, and the order of reactions. In the order of reactions, you have two different kinds of order of reactions. That is zero order and the first order. So in that zero order, you learn about the reaction and the half-life of zero order drugs. And first order of reaction and the first order half-life of the drugs. So I derived the equations for you. So this is the three topics till now I covered. And the next topic for today's class is compartmental kinetics. These are also called as compartment models. Compartment models. The compartmental kinetics are also called as compartment models. So, what do you mean by compartment models? You have to analyze the movement of the drug, right? So, you have to analyze the movement of the drug in the body. So it is very complex process. Why? So if the drug will be absorbed or distributed or metabolized or it will undergo elimination process, it will be very difficult to determine the movement of the drug in the body. So you need a simple method. You need a simple method to derive or to describe or to analyze and to interpret the pharmacokinetic data. So you already have some idea about this pharmacokinetics. So while I'm explaining the plasmid drug concentration versus time profile curve, so what are the pharmacokinetic parameters you read under that? AUC, Cmax and Tmax, right? These three are of major pharmacokinetics of a drug. And what do you mean by dynamics? Onset of action, intensity of action, duration of action, right? Therapeutic window, therapeutic range, all these will comes under pharmacodynamics. So under pharmacokinetics, you have AUC, Cmax and Tmax, right? So after taking a drug in the form of dosage form into your body, so it will undergo various kinds of mechanisms. So it is very difficult to determine the pharmacokinetic profile for such drugs. So you need to interpret the data, you need to analyze the pharmacokinetic parameters, and you need to describe the equations, and you need to derive the equations. So these are all very important. So for that reason, you have to simplify the data for mathematical expression, and to get a quantitative determination, for such reasons, you have to select the PK models. For such that you have to select the various PK models. Pharmacokinetic models will explains you the mathematical expression of the PK data and the quantitative relationship of the PK data in vivo. See, ma'am, whenever you are doing a research or you have to find out a new molecule to know the pharmacokinetic parameters, you need to interpret the data for in vitro and in vivo. So, in vitro means you need to do first majorly in our labs, that is research labs or college labs, whatever it is. This is called in vitro data analysis. Then you have to perform your experiment on animals, on selecting suitable animals. Okay, suppose you want to test oral dosage form, right? So you need to see for humans also in case of transdermal systems, right? So you need to select rats or mice, whatever it is. So that's why I'm telling you the suitable animals you should select to see the in vivo pharmacokinetics. So where you get this in vivo data? By pharmacokinetics only. And for pharmacodynamics and for pharmacokinetics, you need to perform the in vivo analysis of your data. So always there is a correlation between in vitro and in vivo data. That correlation is nothing but IVIVC. This is called in vitro in vivo correlation. IVIVC. V is also there. In vitro in vivo. IVIVC. So always there is a correlation between these two. So without estimating your pharmacokinetic data in vivo, it is very tough to interpret your data between in vitro and in vivo. See how these pharmacokinetic parameters will plays a major role to analyze a new drug or to discover a new drug into the market. So these pharmacokinetics are very important to know the efficacy and therapeutic activity and pharmacological activity of a particular drug. See, suppose if your Suppose these pharmacokinetic models will be classified into three different types. See here, the chart will be here. Methods for analysis of pharmacokinetics data. See, methods for analysis of pharmacokinetic data like Cmax, Tmax, AUC. So these are all pharmacokinetic data. So you can choose the methods for analyzing such kind of data and interpreting such kind of data. Why? Because you need to select these models. Why you need to select these kinds of models? It is very tough to assume that how much concentration of the drug will be enters in your body or distributed in your body. It is very tough to determine. So it is a very complex mechanism to to find out the concentration and amount of the drugs in our body. We need to calculate our pharmacokinetic data of the drug by choosing any one of these models. So what is these models? How many types are there? See, methods for analysis of pharmacokinetic data will be dependent on two types, will be classified into two types, model approach and model independent approach. So what do you mean by model approach? And this will be a particular model. See here. Again, this model approach will be classified into three different types. Compartment models, these are very important. Physiological models and distributed parameter model. So generally, this model approach will be classified into three types: compartment model, physiological model, and distributed parameter model. So in your syllabus, you don't have this distributed parameter model. So you have compartment model and physiological model. Apart from these two models, this compartment model is very important. So your compartment model is again classified into two types, right? Mammillary model and quaternary model. And this physiological model, perfusion limited model and diffusion limited model. And then the model independent approach is non-compartmental analysis. So in your syllabus, you have compartment models, physiological models, and non-compartmental analysis. So you have three different kinds of model approaches in your syllabus to estimate the pharmacokinetic data or to analyze the pharmacokinetic data of a drug. So the methods of analysis for pharmacokinetic data will be classified into two approaches: model approach, model independent approach. Your non-compartmental analysis will comes under model independent approach. In under model approach, you have compartment models and physiological models. Okay, so let me discuss it one by one. Coming to this compartment models. So what do you mean by that? Compartmental analysis is commonly used. These are commonly used to estimate the pharmacokinetic characters of a drug. The compartments are hypothetical in nature. That means homogeneous. Homogeneous. Then see, the body is each and every point is very important. The body is represented as a series of compartments arranged either in a series or parallel to each other. Those will communicate reversibly with each other. See, what is that meaning of that sentence? See here. Your compartment, suppose blood or plasma or liver or lung or kidney. You just assume all these highly perfused. See what I am telling you? All these highly perfused tissues, will be in central compartment. Blood or plasma or liver, lungs or kidney, or these are all highly perfused tissues. So the other tissues, those are perfusion limited tissues, or those are low vascularity, or low perfusion. Those may be attached to this central compartment. So these kinds of tissues will becomes under central compartment, and these low vascularity nature tissues or low perfusion tissues will be said as peripheral compartments. Peripheral compartments. See ma, carefully, just listen. So these all are under central compartment, and this low vascularity, low perfusion will comes under peripheral compartments. Once your central compartment will be joined to this peripheral compartments, the movement of either drug absorption, distribution, whatever it is, the parameter of ADME will be going on. So what is this sentence exactly? The compartments will be either arranged in a series. See, these highly perfused tissues and these low perfused tissues will be arranged either in a series or parallel to each other in a reversible manner. That means it is showing the arrow marks like this. That means it will be a reversible process. This arrow marks will indicate you it is a reversible process. See, the body is represented as a series of compartments. So no, your body is consisting of many organs or tissues, right? So it is consisting of series of compartments. It will be arranged either in series or a parallel to each other. Those will communicate each other by reversibly. So each compartment is not a real physiologic or anatomic region, because you are just assuming that it's not a real physiological region, right? And considered as a tissue or group of tissues have similar drug distribution characteristics. This point is very important one. See ma, What I told you here, those are parallelly joined or serially joined. Those are not exactly physiological regions. Okay, just assuming that regions like 1, 2, 3. Next slide, I will explain you. Next slide, I will explain you that. Okay, so those are not exactly physiological models, but the tissues, those are having same drug, same distribution pattern as your drug. Those are having same distribution pattern of your drug. So how the drug distribution pattern will be, suppose it is having 50 ml per 2 hours or 3 hours distribution capacity. So your kidney is also having same efficiency to distribute the particular drug. So that's why I'm telling you, the drug which will shows the distribution as that of your tissues will be considered. Why? Because if the tissues will be in infinity, it is very difficult to manage or to express the equations in mathematically. The kinetics will be in mathematical expression, right? So if the tissues or organs presence in our body will be infinity, right? So it is very complex to determine such mathematical expression of pharmacokinetics. For that reason, you can select that organs or tissues those are having same distribution pattern to that of your selected drug. The meaning of the sentence is like that: similar blood flow and affinity. And then every organ, tissue or body fluid that can be equilibrated with the drug. Seema, whatever the organ, tissue, you can select that, you selected that this organ or tissue body fluid can get equilibrated with the drug, which will be considered as a separate compartment. The rate of drug movement between the compartments, that is entry of the drug that and exit of the drug. Entry means absorption. See, entry means absorption. Exit means elimination. Is described by first order kinetics. This is also an assumption. Why? Because the drug will be transported between the compartments based on its concentration. So that's why those will follow first order kinetics. Our first order kinetics meaning is that only, right? So these are concentration dependent. So the entry of the drug, that is nothing but absorption of the drug, and the exit of the drug, that is nothing but elimination of the drug, will be described by first order kinetics. And the rate constants are used to represent the entry and exit from the compartment. So here you are going to use, in compartment models, you are going to use some rate constants 1, 2, 3, etc. Those rate constant are used to represent your drug entry and exit from particular compartment. See, how many types of compartment models are there? So you have majorly pharmacokinetic data analysis. You have majorly three types of compartment. First one is compartment model. Next one is physiological model. And the third one is non-compartmental analysis. By the use of these three kinds of compartmental data analysis, you can select first one, compartment models. These compartment models can be divided into two types: mammillary model and quaternary model. So first I will discuss you about mammillary model. See here, it consists of one or more peripheral compartments. Skin, okay. Apart from kidney, liver, lungs, you can select any of the tissues as peripheral compartments. Apart from kidney, lungs, and liver or plasma, these are central compartments. Okay. So these peripheral compartments will be connected to the central compartment. See here, the central compartment comprises of plasma and highly perfused tissues, what I told you previously, such as lungs, liver, kidneys. These are comes under highly perfused tissues, right? So which will be rapidly equilibrate with the drug distribution. These highly perfused tissues will be rapidly equilibrate with the drug distribution. The drug is directly absorbed into the compartment, that is nothing but central compartment. So your drug will be absorbed directly to the central compartment. Drug absorption is directly to the central compartment. That central compartment is nothing but plasma or blood or highly perfused tissues of lungs, liver and kidney. This is very important and very easy. See, elimination. Elimination too occurs from this compartment. Why? Elimination is also occurs from the central compartment only. Why? Because the major organs will be involved in drug elimination are, what are those? Kidney and liver. So these are also present in the central compartment, such that the absorption process and elimination process, these two processes will occur from your central compartment itself, because there is a presence of highly perfused tissues and the elimination organs are also present here. So the highly perfused tissues and therefore presumed to be rapidly accessible into the systemic circulation. And then the peripheral compartments or tissue compartments denoted by the numbers of 2, 3, etc. One is your central compartment. 2, 3, 4, 5, etc. are peripheral compartments. These peripheral compartments are having low vascularity and pure perfusion. Poor perfusion. See here. Peripheral compartments are low vascularity and poor perfusion. So, what you understand from this? Number one, that is blood or plasma or highly perfused tissues. Okay, lung, liver, kidney. So these will comes as a central compartment. Okay, then this central compartment will be joined either parallel or in a serial manner to the peripheral compartment. Right? This is numbered as 1. These peripheral compartments are 2, 3, 4, whatever. Okay, each compartment, first suppose skin, this is number 2. Next, like that. So you have different brain, like that. You have to divided this peripheral compartment. You just give number as a 2, 3, 4, like that. Okay, so either the arrangement may be serial or maybe parallel. Okay, so then this central compartment and peripheral compartment, and this the absorption, the major points I am telling you, and then elimination. These two processes of the drugs will be happened from central compartment only. Okay, then just see, this is the compartment model of mammillary model. See here the arrangement of compartments will be, how it will be? In a parallel model. How the arrangement of compartments? In a parallel model in case of mammillary model. See here, you just consider, before going to know that, you just know IV and extravascular administration of drug. Administration, extravascular means either of oral or of rectal. 1 minute. Or rectal. So, what do you mean by IV? The drug will be directly entered into the intravenous route. So there is no need of absorption. Why? It will be directly enters into the systemic circulation, right? There is no absorption. You just remember, in case of IV routes, there is no absorption. Only elimination is there. Isn't it? Only elimination is there. There is no absorption. In case of extravascular administration, either it may be oral or rectal, those will show absorption and elimination. Right? See, first you find out this difference, then it is very easy. See, ma, here you have one compartment, two compartment, and three compartment. See, each and every rectangular shape of this box will indicate you compartment. See, each and every rectangular shape of these boxes will indicate you compartment. See here, this is one compartment. That is what the number is 1 here. So this is model number 1. One compartment open model of IV administration. See, intravenous administration means there is no absorption. If absorption is there, that will be indicated like this. If absorption is there, see ma here. Here, in case of extravascular, either oral or rectal, you have absorption, right? So that's why the arrow mark is here. This is elimination. So, in case of this one compartment open model, there is a presence of only one compartment, that is by IV administration. It will undergo elimination. Then this is the concept. Then what do you mean by K10? K is a rate constant. I already told you, you have to calculate 2 or 3 number of rate constant depending upon the model. So K10. Why it will be 10? See here, ma. 0 is representing you elimination. K is representing you the compartment. So that's why K10. It's not K01. If it is K01, it will undergo absorption process. See here. Here it is K01. Why? Because here it will undergo absorption process. So that's why this 0 is first. Then only 1 will comes. In case of elimination, first it will comes with 1. After that it will be 0. So if absorption is there, this is 0. If elimination is there, this is also 0. But in between this absorption and elimination, there is a compartment. Okay, before the compartment, if you have an absorption phenomena, you just start the rate constant with 0. Otherwise, you just leave this 0. First, you write one compartment. That means the meaning of this is your drug will be directly enters from the compartment to the elimination in case of intravenous administration. See how simple it is. See ma, how simply I am telling you. So that's why your drug will be transported from the compartment to the elimination. That's why you have to write 1 first, then you write 0. This is of one compartment open model, intravenous administration. Next, come to this one compartment open model, extravascular administration. As I told you previously, you have absorption phenomena and elimination phenomena, right? Here, your rate constant will start from 0. Why? Because the absorption is there. That's why. Then 0, 1 and here 1, 0. So then you have model number 3, that is 2 compartment open model of intravenous administration. So here you have 2 compartments. See here, this is the central compartment and this is the peripheral compartment. See ma, I am representing you P. P stands for peripheral compartment. C stands for central compartment. Your one compartment is central and second compartment is peripheral. there is a commitment of reversible transfer. See the arrow marks here. These will indicated you 1 to 2 either or 1 to 2 to 1. So that's why the constants will be 1 to 2 or 2 to 1. See how the arrow mark will be. It will be traveled or it will be transported from 2 to 1. That's why K 2 to 1. So, and what about this K10? And in case of intravenous administration, there is no absorption, right? So you have only elimination. That's why your 1 is compartment and 0 is elimination. K10. It is very simple. See, and then in case of 2 compartment open model, it will be extravascular. See, same 2 compartments. The drug transported will within this 1 to 2 or 2 to 1. Okay, and here it will be elimination and here it will be absorption. As I told you earlier, the absorption and elimination, both the process will be occurred from which compartment? Central compartment. I told you, no? So this, see this. This is the absorption 0, 1. So 0 stands for here absorption and here elimination. So both the phenomenons will be occurs from central compartment only. Why? Because we have highly perfused tissues in central compartment. That's why, right? So, and then this is the 3 compartment open model. The name itself indicated here. There is a presence of 3 rectangular boxes. That is 3 rectangular compartments. See here, 1, 2, 3. And how the rate constants will be? See, just leave 1. Just concentrate on 1, 2, 3 or 2, 1, 2, 2. See here, 1, K1, 2, K2, 1. And here the constants are K1, 3 and K3, 1. The transport or the movement of drug will be reversible, right? Reversible to each compartment. Here the drug is movemented from 1 to 3 and here 1 to 2. And then coming to this K10, because this is an intravenous administration, there is no absorption. That's why your constant is eliminated here. So you have to write K10. And the next one is 3 compartment open model by extravascular administration. See here. So you already know, you have an idea, right? So wherever the extravascular administration will comes, you have to calculate the absorption and elimination, right? So here drug is absorbing and here the drug is eliminating. So absorption is there, that's why K01 is a constant. And here elimination is there, that's why K10 is a constant, rate constant, right? So here your drug is transported from 1 to 2. So that's why 1 to 2 and here 2 to 1. And here 1 to 3 and 3 to 1. So these 1, 2, 3, 4, etc. are representing you the compartments. So one number is representing you the central compartment. 2, 3, 4, 5 peripheral compartments. So in case of intravenous administration, there is no absorption because the drug will be directly enters into the systemic circulation. It will undergo elimination. It's a very simple concept, ma. See, okay. So that's why you have to consider always whenever the intravenous administration is there, either of 1 compartment, 2 compartment or 3 compartment, you just calculate only the elimination rate constant. There is no absorption. In case of extravascular, you need to calculate absorption also because after absorbing only drug will be eliminated out. So absorption is considered as 0 and elimination is considered as 0. First, in case of extravascular, I am telling you. So first this will be 0, right? Absorption is transported from 0 to 1, that is central compartment. So that's why the constant is K0 to 1. In case of elimination, elimination is going out from where? From 1 compartment to 0. So that's why elimination constant is K10. K10. So just remember these few points. It is very easy to learn these compartment models. Okay. So then the number of rate constants can be calculated. Here you need to concentrate only on two roots, right? One is IV and second one is extravascular, right? So in case of IV, what I written here? The rate constants, the number of rate constants I am telling you, 2n minus 1. See ma, R is representing you the number of rate constants. See carefully, number of rate constants. And N is number of compartments. So how the compartments will be in case of intravenous? There is a presence of only one compartment. In case of one compartment open model. In case of two compartments, there is a presence of two compartments only. In case of three compartments, there is a presence of three compartments, right? So, how you will give the number of rate constant for for IV administration? See ma, 2n minus 1. Every time it will be a minus 1. Why? Because there is n stands for number of compartments, right? Suppose it will be a one compartment open model. Suppose it will be a one compartment open model. 2 minus 1. R is equal to 2 into 1 minus 1. So how much it will be? 1 only. So that represents you the number of compartments. So one compartment is 1 only, na? So that's why the rate constant will be 2n minus 1 in case of IV administration. And in case of extravascular administration, R is equals 2 into n. See ma, in case of one compartment, how it will be? 2 into 1 is equals 2, right? In case of two compartments, 2 into 2 is equals 4. So you have to calculate for rate constant. Shall we check it out? So in case of two compartment extravascular, is there 4 constants there or not? In case of two compartment extravascular, see 1, 2, 3, 4. Is it balanced? Your calculation is balanced or not? See here 1, 2, 3, 4. So that's why here you will get an answer 4. That is what the rate of the R is number of rate constant. So you have to remember this. IV administration R is equals to n minus 1. Extravascular administration R is equals to n. N stands for number of compartments. By knowing these compartments, you can calculate the rate constant. In case of three compartment open model, or in case of extravascular, how it will be? 2 into 3, that is equals to 6. Whether 6 are present or not. See 1, 2, 3, 4, 5, 6. Yes, the calculation is balanced. So likewise, you just calculate the constants. See ma. Then that is about mammillary model. So your compartments arrangement will be of parallel manner. That is what? Mammillary model. Then next one is quaternary model. So you just assume in your brains train. How the train compartments will be? It will be a serial, right? So the C here 1, 2, 3. There is no parallel arrangement. The compartments will be arranged in a serial manner. You just assume a train in your brains. So in this model, the compartments are joined to one another in a series like compartments of train. Like this is however not observable. This is however not observable and physiologically or anatomically. So we cannot assume that our compartments will also be present in this manner, right? So why? Because various organs will be directly linked to the blood compartment. So this will be rarely used. So mammillary model will be commonly used and quaternary model will be rarely used. Why? Because in quaternary model, the compartments will be joined in a series. So we cannot sure that various organs which will be present in our body will be arranged in a serial manner. Either it may be parallel also. So that's why this is a rarely used model. See how the compartments arrangement will be 1, 2, 3. Okay. So the rate constant calculation will be the same manner what I told you in mammillary model. See ma, here it will be absorption and here it will be elimination. Case 0, 1, K1, 0. So here are 1, 2, 2, the movement of the drug from one compartment to second compartment and the second compartment to first compartment. Here the movement of the drug from first compartment to third compartment. It's an intermediate, right? So that's why the constant is 1, 2, 3. Sorry, 1, 3. And the constant is 3, 1. That means there is a transportation of or there is a movement of your drug from first compartment to the third compartment. See, that's why 1, 3, right? So then 3, 1. This is about quaternary model. So this model will have some advantages. It gives a visual representation of various rate process. See, by seeing your visual representation, you can easily find out various rate processes which will be involved in drug deposition process. What do you mean by deposition? Distribution, metabolism, elimination, excretion. Sorry, distribution, metabolism, excretion. It shows particular rate RA. See here, it's a spelling mistake. It shows particular rate constants involved in process. Yes. Useful to predict the drug concentration time profile for both physiologic condition and pathological condition. And it is important to develop dosage regimen. And it is having some disadvantages also. The compartments and parameters bear no relationship with the physiological functions. Extensive efforts will be required to develop an exact model. It's not like that your mammillary model. It is very easy. It is clearly describing you either the drug will movemented from one compartment or two compartment, and it will be considered the route of administration also, right? So either it may be undergo IV administration, it is separate compartment kinetics. Either it may be extravascular, it is also some different. So that's why the mammillary model is having very common model, right? So this is developing exact model which will describe ADME of a certain drug. It is very tough. And the model may vary with study population. It is difficult to interpret the results. Yes, this is what I am saying you. You need to interpret the results, whatever you got for humans and animal models. But this model is not useful to interpret the results between the humans and animal models. So the model is based on curve fitting of plasma concentration with complex multi-exponential equation. So what happened in our first order kinetics? Yesterday I told you, C equals to C0 into e to the power of minus kt. So it is called as mono exponential equation. So previous slide, what I told you, generally the compartment models will follow first order kinetics. Why? There is a movement, those may be traveled based upon their concentration. That's what we had an assumption, right? Those are traveled according to the concentration. That's why we consider as first order kinetics will follow. But in case of this quaternary model, there is a complex multi-exponential equations formation will occur. So that's why this is the disadvantage, and this is not commonly used. This will be rarely used, quaternary model. See here, it is a clear representation difference between this mammillary model and quaternary model. See here, compartments arranged in parallel to central compartment. This blue color indicating this central, this yellow color is indicating you central compartment. See here, this is model 1, that is one compartment. Model 1 is one compartment, and this is two compartment, and this is three compartments, right? So what I explained you previously, same thing is here, just it's a overview. You have to know the difference between mammillary and quaternary. See, in quaternary, the compartments arrangement will be like train. See, this is the difference. The compartments will be arranged in parallel to central compartment, and in case of quaternary, the compartment arranged in a series with central compartment. Right? So this will be attached to the central compartment in a series, quaternary model.